Okay, we're back from part one after a very short break. I grabbed some water. Excuse me, you're going to have to hear me cough it out for a second. I'm trying to reset my throat a little bit. I'm going to wait a little longer on food. But I'm back. I want to crank out another one of these. Since I'm kind of on a roll, my mind is just what it's thinking about right now. And let's see. So we're talking about the twin primes. If you haven't seen part one, go back and watch that, or this won't make as much sense, obviously. But we left off talking about these two surfaces, breaking them down into lines, and showing that if we can find an infinite number of values that are not on these two surfaces, we have infinite twin primes. And we're looking at the surfaces line by line. And we came up with there's a nice easy pattern for all the possible lines that represent values on each set of pairs of rows that are not on those surfaces. And we're going line by line now, and we're starting to talk about that. We're about to generalize it a little bit. So I say it's handy to have a table of these values again, so I show some more of the values here. And so we ended with saying that for each row, there's an increasing number of lines that we can choose from. And we're just going to work with the first. We only need one, though, from each row. So we're just going to work with the first line of each row. For the first row, there's only one, so we have to use that one. For the second row, there's 3. We're going to use the first one. For the next row, there's 5. We're going to use the first one. For the next row, there's 7. We're going to use the first one, and so on. So what you're seeing here, and I'll talk about this in a second, but what you're seeing here on the left, excuse me, are the values that we're using for our lines now that are not, and I emphasize not, on either of those rows or surfaces. So here you'll see the first one that we chose, the 3x plus 2. Here you'll see 5x plus 3. Just like I said, the pattern, 7x plus 4, 9, 5, 11, 6, 13, 7, 15, 8. And that would continue, of course. And all I did here is I couldn't fit more in. It wouldn't look right for the picture. But I wanted to extend out past this first 10 or 20 or however many to the right. So all you're seeing here, this 50 would continue up here after the 47. And this 95 would continue up here after the 92. So I just extended this out to the right longer. But then I just brought it down here so you could just have all those values real quick, because this is going to be handy when explaining some of this stuff for some people, or for me it makes it easier to explain and visualize what's going on. So the general formula of the family of lines that were chosen for each row R, now we're calling the row that we're working with first row, second row, third row, row R, showing the value is, well, we recognize here that this number here in the front, the slope, is an odd number. 3, 5, 7, 9, 11, just the odd numbers in order starting with 3. So that's why you see the 2R plus 1 here. Row 1, when R is 1, you get a 3. When R is 2, you get a 5. When R is 3, you get a 7. So it's the odd row, if you will, and that's our slope. So here you see 2R plus 1 times x. This is slope formula, mx plus b. And our b, the y-intercept that we're adding on, well, for the first row it's 2. For the second row it's 3. For the third row it's 4. It's always 1 more than the row number. So that's why you see r plus 1 here. So here's a general formula in terms of the row that we're talking about now for each of these lines of values that won't appear on that row, or either row for both of those surfaces above. Excuse me. And so then you see that chart here, and like I said, I extended it out. And I just say that the values I've moved, I truncated over and moved them back down here, so you could see some of these values. So that's it. So that's the general form in terms of row number and just a line x, variable x, for all the values on this chart, according to the row number now. Because we're going to have to work with the row number itself and show that these things don't exist between rows, and you're going to have to know the row number. Okay, so here's the general form of this that we're looking at. So now we're going to talk about infinite values in the intersection of adjacent rows. We've built our premise here and our basic idea of what we're trying to do. We've shown it for each row individually. But now we have to, like, before we tackle the whole chart and show that there's an infinite holes or infinite numbers that don't exist in all those lines and rows for the whole chart, can we do it for just 2 rows next to each other? That's like, it's the baby steps, right? So now we're going to talk about the infinite values in the intersection of adjacent rows. When comparing 2 rows, the full intersection of sets is of interest, requiring each line to get its own variable. For the first 2 rows, the relationship is equation 13. So now, what am I saying by that? I mean that the number has to come from this set, this 3x plus 2, and it also has to come from 5x plus 3, but we're not necessarily using the same x here. We could use any x to generate all these numbers, and we could use any other x to generate all these numbers. And when we're comparing the rows, we want those 2 variables to be separate so that we can compare both sets completely. So that's all we're saying here, why I added a y instead of x. We need them to be separate. So we're looking for values that are 3x plus 2 equals 5y plus 3. 3x plus 2, 5, now here's going to be y plus 3. So if a number is in this line, we know it's not on the first row of either of those 2 surfaces. And if it's not on this line, it's not on the second row of either of those 2 surfaces. So if it's in this line and in this line, like 8 is the first one that shows up, or what's the next one, it's going to be 3 or 5 out here. 14, 17, 20, 23 is the next one, so forth and so on. 38 is the next one. Those values are in both of these rows, so they're not in the first 2 rows of either of those surfaces. So that's what you're seeing here. We want the values that are 3x plus 2 and 5y plus 3. And now this has integer solutions for an integer s. So as you can start to see here, the first pair is 8. Because of the relationship between 3 and 5, you're going over. The next one is 23. Then we go over a couple more and we get 38. Then you go over a couple more and it's going to be 53. And again, you got to jump down to the next row. But there's an infinite number because we're dealing with 3x plus 2 and 5x plus 3. There's an infinite number of those values that will be in both of these rows, and then thus not be in those other 2 rows, the original surfaces. And this is what I said. This gets a little tricky to talk about, so bear with me. But it gets very convoluted and very. It's just very tedious, but it's very basic at the same time. So we just want a formula that generates all those ones that meet both of those requirements, and that's what this S is. So this has integer solutions for S. So if you allow x to be 5s plus 2 and y to be 3s plus 1, that will give you those values. So for example, when s is 1, so for s is 1, the first one there would be 7. But then when we plug 7 into here, we get 23. And remember, 23 was one of our values that showed up in both of these lines. So that's what we're starting to do here. We're making the generating function or the integer solutions for this whole set here. Okay, great. So the integer solutions in adjacent row relation are used to calculate the positions and values of the intersection between those rows. And that's what I said. This has been years since I've tried to explain this to someone, and it gets very tedious. So you're going to have to. I know I say it a lot. Bear with me. You're just going to have to, because I'm doing this on the fly, and it doesn't get any easier than this. You can always pause it and read it, or get the paper, or once you know the premise of what we're trying to do, you can jump ahead. For some of you, this will be easy, and you'll say, "Oh yeah, go ahead, go faster," or whatever. So starting with s equals 0. So for the s equals 0, when s is 0, you'd get 2 here. You'd plug 2 in here, and you'd get 8. Or if s is 0, you'd get 1 here, and you'd plug 1 in here, and you'd get 8. And that's what we're showing. And remember, 8 was the first value that we found that was in both of these rows. So starting with s is equals 0 and using the resulting equations shows that the first element in row 2, 8 in this case, will map to the second element of row 1. Okay. So that's what we just said. And again, that every third element thereafter on row 2 will map to every fifth element thereafter on row 1. You can see that here. Every third element on row 2 will map to every fifth element on row 1. And that was the correspondence between the positions of these values. 8, 8 here, second value, first value, and then 23 and 23 is the seventh value and the fourth value, and so on and so forth. 38 and 38, and you can see what's going on there. Okay. So checking the s equals 1 case we already did gives y equals 4 and x equals 7. And we indeed see the fourth element on row 2, value 23, mapping to the seventh element on row 1. The next shared value would be s equals 2. So you're just going up, 0, 1, 2. You're just going through your s's. So when s is 2, with row 2, element 7, value 38, and row 1, element 12, value 38. So this establishes an infinite number of values in the intersection of these two rows, one for each s. So for every time you have an s, you have a value that is in both of those rows. And therefore shows an infinite number of values not within the first two rows of those surfaces. Because now remember that we're only dealing with, this is the stuff that is already not on either row, and then the stuff that's not these numbers, or that are these numbers, will not be on the surface. And rather than me worrying that you guys understand that, I'm just going to have to assume you understand what I'm saying at this point and go on and kind of, because I don't want to have to backtrack or talk about it that way as I go forward, because this gets a lot more complicated in that regard verbally. So I'm just going to have to try to make it work and assume that you can either stop the video or pause or we'll go from there. But let's see. So this establishes the infinite number of values in the intersection of these two rows, one for each s, and therefore shows an infinite number of values not on the first two rows of the surfaces. Using the general formula for the rows from equation 12, this is our generalized equation 12 here, allows for the solution between any two adjacent rows, using rows r and r plus 1 in the same way that we did in equation 13 for rows 1 and 2. So this gives equation 15. So now so all we did was take this same strategy that we did here with our general formula for any row r, and now we want to look at row r and row r plus 1. So here we're comparing the same way we set these two equal, row 1 and row 2. Here we're setting equal row r and row r plus 1. And we did that by plugging that into this general formula here. So using rows r and r plus 1 in the same way that we just did gives us this equation here. And the same way, so for any row r and row r plus 1, you'd use this formula. And the same way we made our generating function here, or our integer solutions as we called it, which can just generate all those values and their places between the two rows that you're talking about, row R and row R plus 1. We came up with this form here between the first and second row. Here's your general form. You'll see that the general form for any two adjacent rows is, instead of x equals 5s plus 2, it's s equal 2 row plus 3 times s plus row plus 1, and y equals 2r plus 1 times s plus r. So again, s is just your generator here, and r is your row number. So this verifies that there's an infinite number of solutions in the intersection of any two adjacent rows, and therefore an infinite number of values not on those two specific rows of the surfaces. So you can take, say you want row 100 and row 101. You plug row 100 here in, and you'll get, and this will be for row 100 and row 101. And then you'd get your generating solution for s, and then you can start plugging in your s's and generating all those x and y values according to this. With your row and your s's plugged in, you'd start generating your x and y values, and those would be values that are on both of those two rows, over and over, infinite of them. All right, great. So now that was for the first two rows as an example, and then we generalized it to any two rows. Okay, well, what about the first three rows now? Can we extend that to the third row? And what we're eventually trying to do here is find this function for all the rows so that we can look at what we're dealing with and say, hey, look, there's an infinite number of values there. We're golden. So how can we look at the specific shared, how can we get a similar function for the specific shared values for the first three rows? Now, the goal is to show an intersection common to all three rows. And again, we don't have to get the entire intersection. We can just work with part of it the same way we work with just part of the lines. As long as it leaves an infinite remainder, we're good. So to do this, it helps to show the common values through the first three rows. And this gets tricky, and I tried to make it best linguistically I could, so we'll see how this goes. But when the term position is used going forward in the paper, it generally refers to the ordinal, or what order number it's in, what order it is, the ordinal value or location of a member within the set. What do I mean by that? Oh, if I just say the first position is the first element in the set, the 10th, the number's in the 10th position, it's the 10th element of the set. That's what I mean by that. The term position going forward generally refers to the ordinal value or location of the member in the set, not the actual value of that element. Okay. This can also be thought of the column in figure 3. And I get convoluted here a bit, but say not to confuse things, rather what would be those values if they were not all offset by 1. So when I talk about the position, I'm just saying, this is something for when I wrote the paper, but I can explain it to you more quickly in words. All I was saying there in this next part is that the position, if I say the fifth, I'm talking about 1, 2, 3, 4, 5. But according to this picture, I said not to confuse things. I have the value of the line out here. So the fifth thing would be in the 6th column here, because I'm using this first column for housekeeping or bookkeeping, or to show what line we're talking about. So of course that confuses things more, and I wanted to say not to confuse things more. This is how I had it set up. But anyway, so that's all I'm talking about here. So we've already shown that the values from the first row, 3x plus 2, are not on the first two rows of the surface. We did that. We also showed that an infinite number of elements will map between any row R and row R plus 1 that is not on that surface. If you were just to pick two rows, you could find an infinite number of values that are not on, that are on the rows of the numbers that aren't, so therefore they aren't. Again, I got to stop doing that and just assume that you guys get what I mean at this point. The question is now, which of those elements maps between rows? So we've shown that there's an infinite number of them, but now we want to get more specific and say which ones are the ones in that row. Like in my example up here, I started to say, oh, the value 23 mapping to the 7th element of that row. The next shared value is row 2, element 7, value 38, and row 1, element 12, value 38. So we're looking at what column it is or which value in the row are the ones that are mapping. So the question is now, which specific elements are the ones that are mapping between those rows? Start by examining the second row, 5x plus 3. Equation 14 showed that the elements that map from 5x plus 3 in the second row into the first row are in those 3s plus 1 positions of the second row. That is the positions 1, 4, 7, and 10 of row 2 that correspond to the values. I tried to make it more explicit here in my explanation. So these are the positions, 1, 4, 7, 10, of row 2 that correspond to those values. And those are the ones that map. So again, the elements that map from that 5x plus 3 in the second row into the first row are those 3s plus 1 positions, because 3s plus 1 was our equation here. Now repeat that question, only this time asking not only which values will map from row 3 to row 2, but which of those values will map from row 3 to the specific values in row 2 that were just mentioned, and thus allow them to also intersect with row 1. So again, we're trying to extend this to 3 adjacent rows and not just 2. So we want the values that map from row 3 to row 2, but we want the ones that map to row 2 in the positions that will then also go on to map to row 1. So we found a value in all 3 rows, if that makes sense. That will also allow them to intersect with row 1 also. So using the general equation with r equals 2 gives the location of the overall elements that map from row 3 to row 2 as the elements in the y equals 5s plus 2 position of the third row. This is where it starts to get tedious. Now, I've checked all this, and I'm going to have to trust what I wrote, and I know it's right for that sense, but I'm just going to read what I have and not scroll back every time and try to show you. You'll have to verify or check what I'm saying is true, but for me to talk about it, I have to kind of just go with what I have here to explain it. So, using equation 16 with R2 gives the location of the elements that map from row 3 to row 2 as the elements in the 5s plus 2 positions of the third row. It also shows that they map to the 7s plus 3 positions in the second row. So the values, the 5s plus 2 positions in the third row map to the 7s plus 3 positions in the second row. And that was from using this equation here. So since it was shown that all 3s plus 1 positions in the or locations in the second row map down to the first. So again, I'm trying to do this a little bit piecemeal for this first one just to help you guys break into it. So we know that so the third row to the row 2 are the 5s plus 2 positions in the third row that map to the 7s plus 3 positions in the second row. But we also have that the 3s plus 1 locations in the second row map to the first. That was what we showed for our example. This means that whenever this 3s plus 1, which I made it an x here again, is equal to this 7s plus 3, I made it a y here again, because that's how it corresponds when you go back and do the math to how we set this up. Equation 17, an element in a 5s plus 2 position of row 3 maps to a position in row 2 that will then go on to map to row 1. So what we're setting up here is we're showing we're finding which ones map from row 3 to certain positions in row 2 that then go map to row 1. So now this has integer solutions in equation 18 for s. And again, not the same s as before, just a general idea. For each of these examples, when we do our integer solutions, I used s. So now we've built a case for the first 3 rows with these integer solutions s. Since there are integer solutions of x equals 7s plus 3 and y equals 3s plus 1, it also means that there's an infinite number of such elements. For every s, starting at 0, we can generate an infinite number of these, and these will all be things that then map to row 2 that will also map to row 1. But see, now here's where it starts to get technical, and you'll have to familiarize yourself with what's going on here in these rows to feel confident about this, or to and I'll try to do this on the fly. Again, it's been a while, but it is complete, so you can verify what I've written here and what I'm talking about. So because of this 3x plus 1 equals 7y plus 3 requirement that we got here, it must now be noted that though an infinite number do map through, not all of the elements in 5s plus 2 positions on the third row will map to a location on the second row that continues to row 1. So what am I saying here? Reiterating, we can generate an infinite number that do with this setup right here, but in that in-between stage, not all of those elements in the 5s plus 2 position on the third row will map to a location in the second row that continues to row 1. There are an infinite number that do, but not all of those elements do. And I guess to try to make this more just intuitive, what's going on here, the easiest way to say this is, at some level, we're just basically dealing with the odd fractions. So if you can think of the first row as the 3 row, and we're dealing with that 3x plus 2, that makes 1 out of every 3 numbers something that we can choose from as our candidate number. But for the second number, we're dealing with a 5 row, and that correspondence between the 3 and the 5 is like 15. You're just looking at common denominators. 3 times. So, for numbers that are in both of the first 2 rows, it's like a 3 times a 5. But now when we also want it to be in the third row, we have to do times 7. So obviously our common denominator is going to grow and grow and grow by 3 times 5 times 7 times 9. And this will come up later. But I feel like we're getting to that part now, so I might as well just say it for those of you who start to see what's going on or understanding what's going on here. So that's all I'm really mentioning here, is that basically what I'm saying is, for each row that we go up, we lose more and more possible values because we have to go by that number of multiple till we get one that does work. But it doesn't matter if we can still find infinite of them and we skip some. We just have to show that there's an infinite number left over. And that's what we're going to end up doing in this case. So even if we waste some and we have to use big denominators, if what we end up with is still an infinite set, we're good to go. So that's all I'm saying here, is that you have to account for this as you go along, and we're going to do that. So again, this gets hard to talk about and tedious and convoluted, but this is the best I can do. As an example, the first integer solution for y is y equals 3s plus 1 with s equals 0. We start usually with s equals 0. That's why I said the first. So if s is 0, that gives y is 1. Since the 5s plus 2 positions in the third row map to the 7s plus 3 spots in the second, it means that the 5, now here we're using our 1, plus 2 equals the 7th element on row 3 maps to the 10th element on row 2. When checked, the value 53 maps between those locations and also continues on and is found in the first row. So again, what we're doing here is, what do I say here? It means the 7th element on row 3 maps to the 10th element on row 2. So if we go back to our chart, we're on row 3. 1, 2, 3, 4, 5, 6, 7. There's the 53. The 7th element on row 3, 9, 10. Adds to the 10th element on row 2. And then that goes on to map to the 11, 12, 13, 14, 15, 16, 17th element or whatever, if I counted it right, on row 1. And I have it down here. I said it right. So whatever I said down here is correct. When checked, the value 53 maps between those locations and then also continues on and is found in the first row. The next solution with s equals 1, gives y equals 4. This translates to this 22nd element on row 3, mapping to the 31st element on the second row. And again, when checked, that value 158 then maps those locations and also continues to the first row. So for the third row, we're talking about value 158 here. But you'll notice that we skipped a big chunk from 53 to 158, that there was some other values in between that would have mapped from row 2 to row 3 to row 2, but then they wouldn't have gone on the row 1. Or there are some other values that are in between that would be on row 2 and go to row 1, but wouldn't have caught anything in that third row. So that's all I meant, is that you start to lose, you're jumping further and further to find one that maps all the way back to the first row, but that's okay. And eventually this will become more clear, and at the end, why we're missing these values and where the other ones are. It's because we're only working with one set of those lines that we had from the beginning, where we chose, in the first row, we have to use the 3x plus 2 line, but for those other rows, we just chose the first line to work with, in this case. So, okay. So that's all we're talking about now, is we're saying that we were able to use that general formula to find the values of our generating function that then make ones that map through all 3 rows. Now, again, a lot of this is pretty intuitive to people at this point. You should say, well, we should just be able to do this like ad infinitum now, and therefore we're going to have values that are not on any row. Yes, that's what we're going to show. That's exactly what we're doing, but we want to establish it a little bit more concretely. And I think other people might see a much quicker way to do this, but this is how I did it, and I did it very tediously and really rigorously and went through it. So now we did the first 3 rows, so now we're going to look at intersections across subsequent rows. So in order to proceed to fourth and subsequent rows, the question must first be answered of which specific subset of elements from the 5s plus 2 positions in the third row map to the proper positions in the second row. So for each step of this, we're kind of going back and forth between saying, there's a stage that says what elements map in general, and then there's a step where you have to say, well, which specific ones map so we can track it all the way back through. And then you go up to the next row and you say, well, what's the formula in general? But then which are the specific ones that hit the values we had from before so that it goes all the way through? So you're seesawing back and forth between the general one for the next row and then going back and saying, what are those specific values? Also, so it's the same thing we did before, but now we're just going to extend it. Also note that the s equals 0 position actually represents the first member of a set. S equals 1 equals the second, and so on. So as such, that ordinal location value of an element within a set is 1 greater than that integer s, when spoken of in terms of being the first, second, or xth element of the set. This is shown as shown in the above example. The first value on row 3 that meets all the requirements is 53. Inserting the 5s plus 2 positions mapping from row 3 to row 2 into the row value of 7x plus 4 for x gives 50. So now we're taking this 5s plus 2 and we're plugging it into this 7x plus 4. Let me just think about that for a second. Which is if you literally plug that in, you'd get 7 times 5s plus 2, which is 35s plus 14 plus 4 gives this. This is why you see 35s plus 18. So inserting those 5x s plus 2 positions mapping from row 3 to row 2 into the row value itself of 7x plus 4 for x gives 35s plus 18. Set that equal to the first intersection of all 3 rows, 53, because that was the actual value, which is equation 19. So now I'm starting to show you how to go back and actually calculate these values from this ping pong process of generate the next row, but then make sure it's the specific values. So when you do this and you set it equal to one of those values, solving this gives s equals 1, which corresponds to the second member of the 5s plus 2 subset, which remember are the positions of values that map from row 3 to row 2. Repeating this process for the next value of 158 gives s equals 4. Again, this is talking about that part that we skipped some, corresponding to the fifth member of that subset. We're only looking for the specific ones that are going to go through. Solving for all values that map back to row 1 gives s equals 3t plus 1 for some other generic integer t, which is just another level of our generating function. Which, again, this gets really hard to talk about, but I'm going to do my best, at least for the concept, to get it through here. You have to just read what I've written here and really start to work through it for yourself to understand what's going on with all these rows. This is why I said it's so tedious, but it's, in one sense, it's not, once you understand what we're trying to do. Which again could also be spoken of as being the 3x plus 2 member of the 5s plus 2 subset for an integer x. Okay, that is, in terms of the members, that the 3x plus 2 positions of the 5s plus 2 locations in row 3 are those that continue to row 2 in positions that will then continue on to row 1. So we're just trying to be able to talk about here which specific elements we're talking about. To help avoid confusion, yeah, right, that's going to be really hard. We're trying. But to make it more explicit, I can start to get into specific values. The 5s plus 2 locations are the columns 2, 7, 2, so forth and so on. And the 3x plus 2 elements, there they are, of those locations are the corresponding columns. And there they are. This can now be put in terms of row 3. And once you do this for a few rows, it becomes clear what you're doing. And you could go through this yourself and duplicate what I said here. And what is written is correct. So if I don't speak about it exactly right, or if it doesn't sound quite easy to understand coming out, try it. Do it, get familiar with it. You'll see what's going on here. And all I'm doing is setting this up for the next few rows so that you can see this general pattern. And then once you see the general pattern, it becomes a lot easier for the mind to say, oh, I get it now. So we're going to get to that. Let me check this here. Okay. So this can now be put in terms of the row 3, 7x plus 4 set directly, and can answer that question at the beginning of this section. Inserting the 3s plus 1 integer relations that select continuing 5s plus 2 positions into 5s plus 2, which remember represents all the positions that map from row 3 to row 2 in general, now puts directly in terms of the 7x plus 4 set only those locations which also map to row 1. This is equation 20. So once you get familiar with talking about which lines and these little sub-generators, represent the positions, and which ones represent the lines, you can plug one into the other to create your overall information that you need. And that's what's going on. We're taking these. So I guess I could say it that way too. If you notice, for any of these that we do for a specific example or even for in the general form, that yes, we're dealing with lines that represent each row, but it also turns out that our generating functions with these s values can be thought of as lines themselves. 7s plus 3, 3s plus 1, and so forth and so on. So you have lines that represent the positions, if you will, of certain values that you're trying to track, and the actual lines that we're using for the rows yourself. And what you end up doing is plugging the actual equation for the lines that represent the positions into the equations for the lines that are the lines you're working with. So that's basically what you're seeing all here is this convoluted conversation about that. And I'm trying to give specific examples and go through it, but that's the generality of what you're doing. So here we've plugged one of those position equations into the line, and we've gotten this bigger form out, 15s plus 7. This states that the 15s plus 7 elements of the 7x plus 4 set are those that map through row 2 to row 1. That is row 3 columns. So if you plug s equals 0 here, you get 7, S equals 1, you get 22, so forth. So this is telling you that row 3 columns this are the ones in row 3 that will map through row 2 to row 1. So now we've used that strategy to track those positions. Now that it is known which values on row 3 specifically will intersect with both rows 1 and 2, and you can go back up in that chart and count over on those columns, and you'll see that those are the 153 or 53 and 158, the values that I was talking about that map through all 3 rows. Or if you were just to extend this out, you'll see that those are the ones that go through all 3 of the first 3 rows. So now that it's known which values on row 3 intersect both rows 1 and 2, this process can be repeated, asking which values on row 4 will now map back to these specific positions. So this is all you're doing. And I'm going to do this 3 more times because it takes 3 more. It depends how fast you see patterns, right? But the overall pattern that we're looking for becomes clear after you've done this up to the 5th or 6th row. Then you kind of really get a feel for how to do what I just did. And at that point you'll see the pattern. And it should become pretty clear here as we keep going. So for each case, you're going to find the general numbers that map, and then you're going to go through and do some calculations to find the specific values so that you can keep generating these bigger and bigger lines that now represent numbers that go through all the first however many rows you've picked. And we want to get to the point where we can generalize that form. So the same way that we generalized back here for any 2 adjacent rows, we kind of want to see what's going on until we can generalize this for any number of rows or all the rows. And that's all we're doing. So here I say now we're going from row 4 to row 3. Using r equals 3 in equation 16 gives the location. So if you go through now, you'll see this pattern. For each row that we're trying to do the next, we use the r that's the row before it because we're going from 3 to 4. So we're using r3 in this case. In that equation 16, our general form. But using R3 in equation 16 gives the location of the overall elements that map from 4 to 3. So here's the overall part. So we're going to use R3 to show which ones map from 4 to 3. And it shows that they map as the elements in the 7s plus 3 positions of the 4th row. Those are the ones that map in general from row 4 to row 3, are the 7s plus 3 positions of the 4th row. It also shows that they map to the 9s plus 4 positions in the 3rd row. Okay. But see, we wanted these ones in the 3rd row that were the ones that go all the way through. So now we have to find the junction between this and this is what we're going to end up doing. This means that whenever these what I just said there, the 9x plus 4, which is this, equals this 15s plus 7, which is this, the y, that an element in a 7s plus 3 position of row 4 maps to a position in row 3 that will then go on to the others. We already said that this one goes through the first 3 rows. So now I think you can start to see what's going on here a little clearer. So when these map to the 9s plus 4 positions in the 3rd row. This means that whenever the 9x plus 4 equals 15y plus 7, an element in the 7s plus 3 position of row 4 maps to one of these, and we're gold. Okay, great. So here again, we know that this is now our new requirement. What integer solutions does this have? So you can look at that. And we're just repeating what we did now, and we're going to get familiar with doing this. Like before, now we have to say the question is which specific subset of elements from those 7s plus 3 positions of the 4th row will map to those proper positions in the 3rd row, these proper positions that meet that requirement. For s equals 0, same as we did before, but now we're using it in these generating functions. That gives y equals 1, and then 15y plus 7 equals 22. So the 22nd value of row 3 and the first value to intersect all rows is 4 rows is 158. So now the way that we inserted the position into the line like we did before, insert the 7s plus 3 position value that maps from row 4 to row 3 into its row 4 element value of 9x plus 5 for x. That's the actual value for that line itself. And you set it equal to 158. You do that to backtrack and get the value that you need, the element, the position that you're looking for. When you do this, solving for s in equation 23 gives s equals 2, which corresponds to the third member of the 7s plus 3 subset. Repeat that process again for your next s. Now we're going to do s equals 1. We just did it for s equals 0. And that gives your next value of 473. And it gives a value of 7 for s when it's used in equation 23. If you had put 473 here. Corresponding to the 8th member of that set. And again, they're off by, you'll see that like the 7 is 8 and they're off by 1 because the s's start at 0, but the number you're talking about is either the first element or second element or whatever nth element you're talking about. So again, you'll have to become familiar with this, but we're just duplicating what we've done now and getting familiar with it. Solving for all these values gives this s equals 5t plus 2, again for some generic integer t. So now we've just said which of our s values do we want. We wanted the second one, we wanted the 7th one. We're generating which s values are the ones we're looking for generic integer t, which could also again be spoken of as the 5x plus 3 member of the set for an integer x. And that's one more because of that thing I just said. The s value and the actual position are one off. This can now be put in terms of the row for 9x plus 5 set directly. The same way we did it before, we put it in terms of the row 3, 7x plus 4 set directly. Now we're putting this in terms of the row 4, 9x plus 5 set directly. Inserting the 5s plus 2, which is this thing we calculated here, integer relationship that selects continuing 7s plus 3 positions into 7s plus 3, now puts directly in terms of the 9x plus 5 set only those locations which also map to row 1. So we've done the same thing we did before now. We've done these two steps of finding the general form, finding the specific values, and then putting it back in terms of what we already had. And you'll see, like before, this new thing we get, 15y plus 7, it's starting to grow. It's just going to grow bigger and bigger. Now we're up to 35s plus 17. This states that the 35s plus 17 elements of the 9x plus 5 set are those that intersect the first 4 rows. And by now you may start to see this pattern or begin to emerge. So the more you do this, you'll get familiar with it, and you can start to then say, well, what's this overall pattern? Can we generalize it? And we're going to. And if I was to take this 35s plus 17 and come way back here, let's get back there for a second. For this 4th row, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 15, 16, 17. So if you took that equation and you looked at those positions in this row, the first one being when 17, the 17th column, which would be 158, you'll see that that value appears in all the rows. 158, 158. We can find it in the second row, 158, and then the third row I don't even have, or the first row I don't even go up to that high, but you can see that that's a form of 3x plus 2. Because 156 is divisible by 3. So that's all we've done now. We're getting familiar with doing this process to finding the ones that map through a specific subset of ones that we know will be on all those first 4 rows. Now, a number might be in the 5th row or 6th row or whatever, but we're building up to all rows. And if we know it's not in those first 4 rows, it's not on those first 2 surfaces in their first 4 rows, therefore it would generate a twin, if it's also nowhere on any higher rows. So we want to generalize that formula for all rows, which is what we're building up to. And here you see we just did it for row 4. We're going to do it 2 more times, and then I generalize it. And I did that to just really drive it home and show people the technique and talk about it. so they can get used to this thing that we're doing over and over again. Although I go a little faster each time, I think, in the paper. Row 5. Using now we should start to be familiar with our pattern. We're starting with r equals 4 this time. Last time it was r equals 3. Using r equals 4 in equation 16 gives the location of the overall elements that map from 5 to 4. Same thing. You should start to be getting familiar with this. They tell us that it's the elements in the 9s plus 4 positions of the 5th row. It also shows that they map to the 11s plus 5 positions in the 4th row. So now, whenever that 11x plus 5, this part, represents this part, is equal to that thing that we just built up, because we have to continue our pattern, that an element in a 9s plus 4 position of row 5 will map to a position in row 4 that will then go on to map through to row 1, because we've already shown that all these other ones go back to row 1. So we're just adding the next part of the chain here, and then we're going to try to look for a pattern in these outputs that we're generating, which will become clear that there's a pattern, where we don't have to just sit here and try to calculate all these values. We can figure out the pattern for them. Okay. So we set these equal again. We find the integer solutions for our next set of s and t that we're going to use to calculate these values. As previously, the question now is which specific ones are the ones that we want? Which specific subset of elements from the 9s plus 4 positions of the 5th row map to the proper locations in the 4th row? We're going to do s equals 0 and s equals 1 again, that whole thing. So when s equals 0 in equation 26 gives y equals 5, and then 35y plus 7 would equal 192. The 192nd value of row 4 and the first value to intersect 5 rows is 1733. You actually calculate that value. Insert the 9s plus 4 position value that maps from row 5 to row 4 into its row 5 element value of 11x plus 6 for x, and set it equal to that value, 1733. Solving for s in equation 27 gives s equals 17. So now we need to find our general equation for all those s's that will be the ones that we want, which corresponds to the 18th member of that subset, the 9s plus 4 subset. Remember, they're one different. Repeating the process for s equals 1 gives the next value of 5198. Plugging that in, you can calculate that gives s equals 52. And then you can use in equation 27, corresponding to the 53rd member of that subset. Solving for all the values gives that relation 35t plus 17. Now that's our line that just gives us all our positions for our s's, for our generic integer t, which again could be spoken of as being the 35 plus 18th, one more member of the set for an integer x. Great. This can now be put in terms of the row 5, 11x plus 6 set directly. Now you're just starting to see this pattern that we're doing, this operation and this technique that we're doing to build these numbers. So now we're going to insert that thing that we just figured out for our t value into the actual line value to give us, that selects the continuing 9s plus 4 positions into 9s plus 4, and that will put it directly in terms of that 5th row, which is the 11x plus 6 set. Only those locations which also map all the way through to row 1. This is equation 28. Not 828, just equation 28. So when you plug that one generator into the line, you see that it equals this 315s plus 157. So this states that the 315s plus 157 elements of that 11x plus 6 set, which is the 5th row, are those that intersect the first 5 rows. And we're going to do one more, and then we'll be able to generalize it. And maybe some of you can already, or again, I think other people would find much easier ways to do this, but this is the way that I was able to prove it to start. So I'm probably, because I'm coming up on my second hour here in second video, I'm probably going to try to get through row 6, and then we'll see if that's a good starting point, and then we'll talk about the general formula for all rows in the third video. I'll start a third video. So at this point, the technique for finding this next set of values is kind of established, and a general formula can be described. When doing so, it's also helpful to have the information from row 6, and rather than walk you through the whole procedure again, the associated equations for row 6 are simply provided. So leading up to this point, I've just kind of done it over and over and over, and I'm trying to make it clearer and clearer and show you But here I just provide, here is, hold on, I got a cat jumping up, messing with the computer while I'm doing this. Come on, buddy. So, same way we did here, which we started off with these two we had to set equal, then we had to get the generating functions, then we had to do this little bit and get this little bit. That's what you're seeing here. Here's the two that we set equal. Here's your generating functions. Here's, one of the values that you use to calculate the t relationship for the ones that are just the position that you want. And plugging it right back into the line itself gives you the values that then map all the way through and show you that next function that you're looking for. It's 3465s plus 1732. Great. So now we're going to look for the general formula for all rows. And I think this is a perfect place to stop before I make part 3. So I'm going to stop the video here. And again, I know some of that, which S plus whatever row, whenever it gets tedious to talk about it, you have to get familiar with it to do it and really follow what I'm saying. But I hope, and again, the paper is accurate. So if you take the time to get familiar with this, I think what we're doing here, I hope I've made it clear at this point, what we're trying to do is find these values for all the rows. This is the cat. You're hearing the mouse thing because the cat is messing with my mouse as I come over. Come on, buddy. Let's go, dude. All right. I got to pet the cat. Oh, come on. This is a perfect place to stop because I miss having cat and mouse issues and everything. But, so that's all we're doing now. We've established this technique for finding the values that are kind of like if you think about it, like our common denominator row values between each row. We're getting familiar with talking about which lines represent the positions of elements in the row and the lines that just represent the row themselves, and combining all that data to give us something that will be, the first 5 rows is what or 6 rows between the 5th and 6th row is what you're looking at here, or the 6th row. And hold on one second. And so now what we're going to try to do is this result that we get each time, this here, and for here it was this one here, and so forth and so on. Can we see a pattern to that so we don't have to do this the whole time? Can we just generalize it now that we kind of get what's going on? And so that's what we're going to pick up next time. So I hope you're able to follow this if you really take some time with it, or I hope you're enjoying this. This is for math heads, people who really like math and tedious arithmetic and stuff. But if you have any questions, feel free to leave them in the comments, or again, maybe I can make some more content. Or if somebody thinks that they can help clean this up and make it, easy, more explanations, I'm down to working with people and give better, quicker explanations. Like I said before, once you understand what you're trying to do here, I think people familiar with modular arithmetic would actually probably find quicker and easier ways to show some of this stuff than I could or did. But let's stop here. I'm going to take another quick break, and I think I have it in me to make another one of these for another hour, half an hour, whatever. It's going to be a bit yet. Probably, although we're getting through it. So if I feel I can do another video tonight, I'll make one more and I'll start getting these up online. I haven't posted the first part yet, so you'll end up being part 1 and part 2 will just be right up there right away, and it looks like part 3. But I'm going to take a little break, and thanks for watching about the twin primes, and we'll see you on the next one.